Okay, so we've been talking about reactions, different order reactions. We're talking about a zero order reaction here. Again, what that means is that there is a rate law, right? And the rate law always looks like what?
You're asking me?
Yeah.
Well, you start with rate equals the reaction, the rate constant.
Right? And then for a zero order, what's next?
Well, I guess concentration of some reactant, right?
All right, but if it's to the zero, then what?
Oh yeah, so that just cancels out. So the rate is just equal to the rate constant.
Very good. And that's the kind of thing we need to recognize when we have a question like this that says, what are the units for a rate constant for a zero order? The units for the rate constants can change and do change if it's zero, first, second, third order, and so forth. And if it's zero order, then that means that the rate equals 2K, and therefore their units have to be the same. Now, do you know what the units for the rate are generally?
Molar per second.
That's right, molar per second. And therefore, K has to be molar per second as well if we have a zero order reaction. Okay?
Oh, I got that. All right, good.
So, what's the starting quantity of if 2.5 molar remain after 5 hours at 2.3 times 10 to the minus fifth molar per second? All right, I think you guys should be able to do this by now. You might have to go back to your last lecture notes a little bit or look at the integrated rate law for a zero order reaction. Okay, so if you can do that now, I'll push pause, answer that question, and then we'll get to it. All right, make sure you gave yourself a chance to answer the question. So how do we do this one?
Well, the zero order integrated rate law is concentration of A will equal concentration of A initial.
Very good.
Minus KT.
Very good, where K is the rate law and T is how much time has passed. Excellent. So if 2.5 remain, which one is that?
That's the AT, or the one on the left.
Okay, very good. So this is A at this time T, right? The concentration of A at time T. So 2.5 equals, and we're trying to find out how much we started with. All right, and then the rate?
2.3 times 10 to the minus 5.
2.3 times 10 to the minus 5, and that's molar per second, right? And so, I mean, we write the units down there because we need to make sure then that our time is in what?
Oh, seconds.
That's right. So I'm going to take my 5 hours and multiply that by 3,600, and that gives me 18,000 seconds. Now I can multiply that by 2.3 times 10 to the minus 5, and that'll give me the a value there, which is basically how many molar, have disappeared over that amount of time. So if I take my 2.5 and add that 0.414, because this is subtracting there, so add that 0.414, then I'm going to get 2.914 as my initial amount of material that I had. Okay, good job. So, first order reactions. First order reactions are different than zero order reactions. Let's do a review here really quickly of what a zero order reaction looks like in terms of concentration of A versus time. What did we say a zero order reaction looks like?
Oh, I can't remember.
Well, zero order reaction, you start with some A, but then over time, that A decreases, but the decreases is linear. Because again, that rate, which is in change in Y over change in X, molar per second, that's the rate at which the concentration of A is disappearing. So the slope is that rate, and that's why we can use that zero order integrated rate law to identify the relative concentrations at any given moment in time, right? It's just related to that slope there. However, in a first order reaction, a reaction that is dependent on the concentration of A in its first order versus time, the rate will not be the same, because as the concentration of A changes, the rate law is going to look something like this, right? What's the rate law for a first order reaction going to look like?
Rate equals K times the concentration of A to the 1.
That's right. And so we see that the rate is dependent on the concentration of A. So as the concentration of A changes, the rate will always be changing. Okay? And there is another very interesting thing that happens with a first order rate, and that is a first order, a reaction that is first order, dependent on concentration of substrate, and that is that the relative amount of A will be halved at a fixed time interval, and we call that a half-life. So let me draw that a little more precisely here. If I have concentration of A versus time, and I start with this, let's say that's 100% of my material, it'll take a certain amount of time, just like any reaction, for me to end up with 50% of my material, right? And that time, we'll call that T1 half, we'll call it a half-life. Now, the amount of time that it's going to take to go from 50 to 25%, or half of how much I'm starting with from this point, will be equal to that first half-life. Another half-life there. And then the time for it to start from 25% and go down halfway again, 12.5% here, right, will be equal to, again, another half-life. So what we see is that there is this cool relationship that utilizes a natural decay in material, and the way that this is described in nature is with a number, just like pi. Remember what pi describes?
Is that the relationship between a circle's circumference and its diameter or radius?
That's right. Pi is that relationship, right? And that's, it's a fixed number because no matter what your circle looks like, that relationship between the radius or the diameter is always the same relationship. Well, there's a similar relationship for these natural decays like this, and the letter is E, or that's Euler's number, and the natural log is the log of E. And so we see this really cool relationship where you have, if you have the natural log of the concentration of A versus time, then for a first order reaction, right, for a first order reaction, then what you'll see is a linear relationship, a linear decay of the natural log of the concentration of A versus time. Okay? So what that results in is our integrated rate law being this relationship. The natural log of the concentration of A initial over the concentration A at any given time, all right, being equal to K times T. K times T, the rate law times time. All right? So there's our integrated rate law. Here's an example of a problem. We're told that it's radioactive decay. Now, in this question here, it doesn't say anything about the order of the reaction. It doesn't say anything about, give us the units for the, well, it does actually right here. See, right at the end here, it says the units for the rate constant in per seconds. Now, that actually is another way we can tell that it's a first order rate law because, again, the rate law is going to look something like this, and if we don't know if it's zero order or first order or whatever, then we don't know what that x is. But if the rate units are always what?
Molar per second.
Very good. And if the units for K are per seconds, 1 over seconds, then that means we have to get the molar here and just one of them. And so that means x is 1, so that means it's a first order reaction. All right? But they wouldn't necessarily need to tell you that because they have also told you that this is a radioactive decay. And all radioactive decays are first order reactions. They have half-lives, right? fixed half-lives. Everything can have a half-life, but a fixed half-life means every half-life you decrease by half your initial amount. All right, so a new atom occurs so that after 21 days, the original amount is reduced to 33%. And we want to know the K for this reaction.
Well, if you have your equation there, the initial concentration could be 100%.
That's right. You could go, for example, the natural log of 100 over 33, right? Because that's how much is left over.
Yeah, and then times K times T. Now, T needs to be in seconds, though, so 21 times what?
Well, 21 times 24, right? That's for hours, and then times 3,600 gets us to seconds. So 1.8 times 10 to the 6th, 1.81 times 10 to the 6th, and that's seconds. Okay, so natural log of 100 over 33. Do 100 over 33 first. Natural log of that value, 1.1. And then we're dividing it by 1.81 times 10 to the 6th. All right, so we got K having a value of 6.13 times 10 to the minus 7. Okay, very good. All right, now as we said, the half-life of a material is fixed for a first-order reaction. Now let's look at a zero-order reaction to compare it really quickly. Because you can have a half-life. Half-life is just how much time it takes. So if you plot concentration of A versus time, right? And that's what this is up here. This is concentration of a reactant in a first-order reaction versus time. This plot down here that I have is a concentration of A concentration of A versus time for a zero-order reaction. It's linear, you can see, so that's how we know it's a zero-order reaction. And I'll write the word zero here to remind us. How much time it takes to get half as much as we started with, that would be that much time. That's my half-life. However, for the next half, to go from here down to there, it's only going to take half as much time, right? And the next half, it's going to just take a quarter of that amount of time. So the half-life for a zero-order reaction is not fixed. Neither is the half-life for a first or second-order reaction. But the half-life for a first-order reaction is always the same. Okay, very good. So how does the half-life, T1/2, relate to K for a first-order reaction? Well, we have our integrated rate law here. And if we put in, because A at time T for T equals 1/2, or T1/2, the half-life time, this concentration is always going to be half of what you started with. Therefore, this ratio, A naught to 1/2 A naught, is always going to be 2, right? If this is 100 and this is 50, right? If you start off with 70 and you go to 35, right? That ratio is going to be 2. So it turns out that the natural log of 2 is equal to K times your half-life. Or in other words, the natural log of 2 divided by K equals your half-life, or the natural log of 2 divided by your half-life equals K. All right? So that becomes a nice tool for us to use. All right. Good job. We'll see you next lecture.